So, excellent talk, Professor Polikoff. Thank you very much. Any questions from the floor?
So I'd be very disappointed if there are no questions.
Good.
There's a mic.
Oh. You showed a slide about the acrylic acid, and that you do the reaction with increasing temperature, but there was no temperature scale in the graph. What temperatures are used?
The reason why there's no scale is not because it is entirely secret, but at the time I made it, I couldn't remember what the precise temperatures were. That graph goes up to somewhat more than 250 degrees. So this is heating water under high pressure. The critical temperature of water is 374 degrees centigrade. I have a car with a number plate W374. When I saw it in the shop, I knew it was the car for me. It's now getting very old, but I don't want to sell it because my research may start going badly if I sell it. But the water, unlike carbon dioxide, as you heat it up, its properties change quite substantially. And water, when you have it at room temperature, dissolves salts, but you can't dissolve organic compounds. As you heat it up, the hydrogen bonds begin to break. So by the time you get to about 300 degrees, water is much more like an organic solvent, like acetone. And when you get to the critical temperature, you can dissolve organic compounds, but salts precipitate. So water is completely transformed, and you have this whole range of properties that you can exploit. The other thing is the water dissociates more at high temperature, so it becomes more acid, but it also becomes more alkaline. So you have this strange effect that it's both more acid and more alkaline than ordinary water, but it is still neutral in the sense that the concentration of acid and base is equal. So you can get acid catalyzed reactions, you can get base catalyzed reactions in high temperature water.
Yep, Professor Annis.
Thank you for a very enjoyable talk, Professor Polikoff. I was very intrigued by the green chemistry building and the green chemistry facilities. Are there sort of quick fixes for existing labs that one can do relatively inexpensively, because that would allow perhaps an even much faster, broader impact?
Well, I'm sure there are some things that can be done. For example, and this really is still slightly surprising. It was discovered that by reducing the airspeed in our fume cupboards, they worked better. So actually by turning them down, you actually got more of the air going out. The trouble is that otherwise you get terrific turbulence, and actually some of the smell comes out into the room. So that there are things you can do by optimizing the performance of your fume cupboards, by switching off fume cupboards. A lot of people use fume cupboards to store smelly chemicals. If you put your smelly chemicals into a small number of fume cupboards, you can switch all the other ones off. And even hard-working students don't normally work more than 12 hours a day, so you could save half the cost by switching off the fume cupboards at night. So there are a lot of things you can do. The other thing you can do is to switch off your computers, which is another, and so on. So there is quite a lot that you can do, but in this particular case, what GSK wants to do is to construct a new building that can be used almost as a sort of test lab, so that they can measure parameters on the building, and all being well, they can then duplicate this building at their various research sites across the world. Because they've made a pledge by, I can't remember which year it is, 2025 or so, that the entire company is going to be carbon neutral, so they want to do.
Yep.
I'm very interested by your idea of cloud chemistry. I wonder if you can tell us more about it, because from the simple, quick description, it more sounds like a outsourcing experiments in China. So
No. It's the opposite, actually, in the sense the Chinese are outsourcing experiments to nothing. No, the idea is, well, reactors, the sort that we use in our lab, are already have a high degree of automation. And so my students sometimes check on their experiments and operate them from home at night. And they're enthusiastic enough before going to bed, saying, I just wonder how my experiment is going. And so the idea is that you can operate them from the distance. But the important thing is that these reactors are quite specific. And if you take industrial research labs that decide that they would like to do a continuous reaction, at the moment what has to happen is that they have to decide we will buy such and such a model of a reactor, and they may make the wrong choice. But my idea is that what they could do is they could rent time on people's reactors all over the world and try out the reaction on different reaction configurations. But it is fundamentally different from outsourcing. Outsourcing is when you say to me, or I say to you, I've got this reaction I want done, go away and do it, and I will pay you some money and you tell me the result. The problem is that when I get the result, I don't really know any more about the reaction. But if I could operate the reactor myself, then I realized, well, if I turned up the temperature up a little bit more than the temperature I had suggested, perhaps it would work better, or so on. And so the idea is that people will get some understanding as well as actually doing the reaction. And in the end, one could imagine having centers for continuous chemistry where they have technicians who can maintain the equipment and so on, specialized technicians, and people can then dial in and do the experiments and so on. But what one would hope in the end is that when you do an experiment, that at the end you would not only get the results, but you would get a mathematical model of how the reactor behaved, so you could then start fiddling around with the model at home and modeling the reaction some more. But it's certainly not the idea of outsourcing experiments to China. It's the exact opposite, actually. The problem on our Chinese campus is they don't have any chemistry facilities at the moment. And this is quite an expensive thing to create. But they could do it the other way round. And I don't know what is in-source, perhaps is the opposite of outsource. So they could source back to the UK.
Yep.
Could you use your hood?
Could
Our students use your hood.
In principle, yes.
So there is two hands and we tell the hand what to do.
Well, in principle, no, but you could, there's no reason why you can't have robots doing things, and
So we don't have to.
no.
Yeah, for this cloud computing, either you have a real person at the other hand to deal with some of the physical operation, or has to be highly automated at the other hand. Yeah. But I like the term cloud. I'm from computer science, so everything with a cloud in front involves the internet. But if you have too many clouds, it becomes a thunderstorm, like what we had yesterday. It could backfire. But, yeah. Any other questions? Just one more follow-up on Professor Ellis' question about this energy neutral or environmental neutral chemistry building. Looking at the material, many of them seems to be quite flammable, but how will you prevent it in a chemistry building, or when you add the anti-flame proof, would it add to the...
Well, I think the answer is that, well, current chemical buildings are quite flammable as well. I don't know if you've ever been in a chemistry building that's on fire, but it's quite frightening. The fire is by far the biggest danger in a chemistry building. There was a really bad year, I don't know, about 5 years ago, where 5 different chemistry departments in the UK had fires in 1 year. And certainly in our building, there was a fire quite a long time ago, maybe 15 years ago, and within less than 2 minutes, most of the building was full of black smoke. And so there is an enormous amount that will burn in the chemistry department anyway. So I think, in a funny sort of way, if you're designing a building where you know that some of the things might burn, you probably design it more carefully than in a conventional building. And but I think there will be less use of plastics than in some buildings, and much of the smoke in our building came, when it caught fire, came from plastics that were burning.
Okay. Any other questions?
Yeah,
Yes, Professor Tao.
Thank you for a fascinating talk. I just want to know a bit more about this carbon storage and carbon capture idea, because at one time when I first heard about it, it seemed that it's going to be the way forward for the industry here. But somehow it seems to come quiet down now. So when I was wondering whether there's some really serious sort of limitations to that idea, or having that a lot more popular than it is now today.
So I'm not an expert in this area. The problem is that it takes a lot of energy. And in a power station, the efficiency will drop by about 10%. This means a modern power station might be 45 or 50% efficient. So that means it will drop to 35 or 40% efficiency, mainly because of the energy of compressing the carbon dioxide. But certainly in Europe, governments are very serious about capturing CO2 and then pumping it, probably burying it under the sea. For example, in the UK, we have the offshore oil fields, which are now depleting, and there may be some actually commercial sense in putting carbon dioxide there, because this may help enhanced oil recovery and get a bit more oil out of these oil fields. So I think people are being very serious, not only for power generation, but also for things like steel making, which generates a lot of CO2. And so it's in the UK, there is still a lot of research, and things are moving forward really quite quickly. What I should say is that there's a huge danger from the pipelines compared to the pipelines from natural gas, because not only is the pressure higher, but natural gas, methane, is lighter than air. So if the pipe breaks, the methane will go up. CO2 is heavier than air, so if the pipe breaks in a valley, you could fill the valley with CO2 and suffocate everybody. So there are quite serious safety problems. So there's one quite important point I would like to make to the young people here. I think it's very important, because you're here in Hong Kong, which is a sort of interface in some ways between European and Asian cultures, to realize that in science it is enormously important for young people not to respect professors. There is a great problem that I have seen in China, Japan, other countries, where the students believe everything the professors say. But you have to realize that, first of all, professors are very busy, and they may not know everything about your experiments and your work. And secondly, they're old and may not understand things properly. So if you have a good idea or you think the professor is wrong, obviously you must be polite and not just say rubbish, but you have to be very firm in saying what you believe is true. And I think it is a really serious problem in some Asian countries that the students always believe the professors when the professors are wrong. So if you learn nothing else from my lecture, learn to say no to the professors in a polite way. Thank you.
Thank you very much. So finally, we would like to present a souvenir to Professor Polyakov to show our appreciation for him to come to CTU all the way from Robin Hood County and to present this excellent lecture to us. Thank you.
Thank you very much. That's very nice.